So let's talk about how some of these decay schemes actually work in radioactive decay. Some atoms have a nuclei that can exist in excited state. And this is not an uncommon thing, but most nuclei that end up in an excited state as part of radioactive decay immediately go back to a ground state, and they don't exist in that metastable state for very long. When they decay to that ground state, they release a gamma ray photon. It comes from the nucleus there as that atom goes from that excited state down to its ground state. Now, radionuclides that can exist in that excited state for a relatively long time, and we're talking about a relatively long time on the atomic scale, so greater than 10 to the minus 12 seconds, are referred to as being metastable. Right? And the most important metastable radionuclide that you should know of that decays via isomeric transition is technetium-99m. As a matter of fact, technetium-99m, the M is for metastable. And clearly technetium-99m, right, it's a real outlier there because this exists in that excited state for quite a bit of time, right? We've talked about the fact that its half-life is around 6 hours. What's nice about isomeric transition? Well, we get decay to that stable state and we get this release of this gamma ray. So that gamma ray is given off. Here we see that happening. That's labeled 1 in this picture here. Sometimes we don't see that gamma ray produced. Sometimes that excess energy in the nucleus gets transferred to one of these orbital electrons, typically a K-shell electron here, and we get what are called these internal conversion electrons, these electrons which are going to head off with kinetic energy that would be equal to what this gamma ray energy would have been minus the binding shell energy of that electron, these internal conversion electrons. Unfortunately, they're going to deposit dose in the patient, right? The negative effect of this here. And once that's gone, of course, the characteristic X-ray production can occur, right? Where this L-shell electron is going to come in and fill that slot and give rise to that characteristic X-ray. Or sometimes this energy difference gets imparted to an outer shell electron and we get the production of those Auger electrons. So things that we've talked about before. But in isomeric transition, the main thing that happens is the rise of this gamma ray here. And as a matter of fact, in technetium-99m, 88% of the decays result in the production of this gamma ray here. Only about 12% of the events result in internal conversion electron. Of course, we'd love it to be 0, right? Because that would be less dose in the patient.